Welcome to our presentation on generative AI, where we explore how machine learning is reshaping creativity and technology. This cover introduces the theme of human-machine collaboration and innovation, and the image hints at creative systems producing art and media. Over the next slides, we'll unpack what generative AI does, how it works, and why it matters across industries. This slide lays out our agenda for the session, guiding you from foundational ideas to technical building blocks, real-world applications, and the ethical questions that follow. We'll start by defining generative AI, then look at key models and algorithms, review industry use cases, discuss challenges and governance, and finish with likely future directions and practical next steps. Now we begin this section on understanding generative AI, taking a moment to set a clear foundation before diving deeper. In the following slides, we'll define what generative systems are, explain their core mechanisms and common architectures, and contrast generative approaches with traditional analysis of focused AI, so you can see why generation is a distinct capability. Generative AI refers to systems designed to create new content, text, images, audio, or video that resembles human output by learning patterns from large datasets and sampling from those learned distributions. Common architectures include transformers, diffusion models, VAEs, and GANs, and the key difference from traditional AI is that generative models focus on producing realistic novel outputs rather than just classifying or labeling data. This slide summarizes the main types of generative models and their strengths, from GANs that excel at photorealistic image synthesis to VAEs that give stable probabilistic latent representations and autoregressive transformers that model sequences for text and code. Each approach has trade-offs in realism, controllability, and scalability, making different models better suited to particular creative tasks and applications. The history of generative models stretches back to early probabilistic approaches in the 1990 seconds and accelerated with breakthroughs like GANs around 2014 and later transformer and diffusion innovations. This timeline image highlights key milestones and shows how advances in compute power and data availability enabled the multi-commodal capabilities we see today, paving the way for richer content generation across domains. Here we introduce the key technologies and algorithms that power modern generative systems, preparing to examine the specific families of models. We'll walk through how adversarial training, latent variable methods, and attention mechanisms each contribute to generation quality, efficiency, and control, and why they matter when building production systems. Generative adversarial networks train two networks in opposition, one generator creating samples, and one discriminator judging authenticity to drive increasingly realistic outputs. GANs are known for higher fidelity image and video generation, and progress is measured with metrics like inception score and Frechet inception distance. The diagram on the slide shows the adversarial loop that fuels continuous improvement during training. Variational autoencoders encode inputs into a probabilistic latent space and decode samples back into data, enabling smooth interpolation and controlled generation between data points. VAEs are valuable for stable training, anomaly detection, compression, and interpretable latent manipulations, offering a different balance of control and realism compared with adversarial approaches, as the illustration on the slide suggests. Transformer-based models rely on self-attention to weigh relationships across tokens and capture rich contextual representations without recurrence, enabling scalable training on massive datasets. These architectures underpin major NLP breakthroughs in generation, translation, and summarization, and they also extend beyond language to image generation and protein folding, showing broad multi-modal applicability. Now we move into applications across industries to see where generative AI is already making an impact and where it's heading. The upcoming slides will cover creative content production, healthcare and research, business and entertainment, and how these technologies change workflows, costs, and possibilities in each sector. In content creation, generative AI powers text generation, like chatbots and writing assistants, image synthesis for rapid design mockups, audio creation for music and voiceovers, and video generation tools that accelerate editing and animation. These capabilities reduce production time, enable personalized experiences, and open new creative workflows, with the slide icons illustrating the variety of media formats that models can now generate. In healthcare and research, generative models accelerate drug discovery by simulating molecular structures and suggesting promising compounds, enhance medical imaging and rare disease diagnostics by synthesizing scarce data, and enable privacy-safe synthetic datasets for research and personalization. The lab image reinforces how these tools can speed R&D and improve diagnostic sensitivity while protecting patient information. In business, marketing, and entertainment, generative AI streamlines campaign production at scale, personalizes customer experiences by tailoring content and timing, assists creative teams in concepting visuals and copy, and helps studios build immersive worlds and characters. These applications can drive higher engagement and faster go-to-market while changing how creative teams collaborate with AI tools in the loop. This section introduces the challenges and ethical considerations we must confront as generative AI spreads, framing issues like bias, misinformation, IP, and societal impacts. The next slides break down specific risks and practical mitigation strategies to help guide responsible development and deployment across organizations and regulators. Generative systems can reproduce and amplify biases present in training data, affecting language, imagery, and decision-making, while also enabling deceptive content like deepfakes and manipulated media. These harms often disproportionately affect marginalized groups, so mitigation requires rigorous dataset curation, fairness metrics, transparent evaluation, and governance to reduce bias and combat misinformation at scale. AI-generated content complicates traditional authorship and ownership, raising questions about who holds rights when models synthesize new works from existing data. Legal frameworks are evolving slowly, so provenance, clear licensing, attribution mechanisms, and enforceable opt-in or opt-out policies are important tools to protect creators while allowing innovation, as suggested by the intellectual property visual on this slide. Societal implications include the potential for job displacement alongside new roles that require reskilling, making workforce transition plans and safety nets important. Responsible use and oversight emphasize transparency, accountability, and human-loop controls, while equitable access and policy engagement are needed to ensure the benefits of generative AI are broadly shared rather than concentrated. This section shifts focus to future directions, highlighting where generative AI research and applications are likely to move next. We'll cover anticipated improvements in model capabilities, tighter integration with other AI methods, societal impacts, and pathways for responsible adoption and collaboration. Looking ahead, models will become more creative and contextually aware, with seamless multimodal integration across text, image, and audio, enabling richer, interactive experiences. Expect more efficient architectures that scale better, improved common-sense reasoning, and real-time human-AI co-creation workflows that let people and models collaborate responsively in practical settings. As illustrated by the iconography on this slide, generative AI will increasingly be combined with other AI technologies, from reinforcement learning for adaptive decision-making to symbolic methods that improve interpretability, and edge or IoT deployments for on-device generation. Robotics applications will fuse perception, planning, and human-robot interaction, expanding capabilities in physical environments and enabling new forms of autonomous collaboration. The broader impact on society and the workforce will blend automation of routine creative tasks with augmentation of human roles, shifting labor demand, and highlighting the need for reskilling and upskilling programs. Inclusive adaptation policies and proactive planning can help ensure displaced workers find new opportunities while organizations and policymakers design fair, accessible transitions. In conclusion, generative AI is reshaping creativity and innovation by blending advanced technologies with practical applications across industries. While progress brings transformative benefits in productivity and expression, it also raises ethical and governance challenges that require vigilance. Embracing responsible development, transparent practices, and equitable policies will be key to unlocking the full societal value of these capabilities.